If you want to approximate R prime at 2, we talked about this. That means you just got to find slope on the interval where 2 is. So you always write what you're approximating. R prime of 2 is approximately equal to. And you could, if you want to do this, we're doing R of 3 minus R of 1 over 3 minus 1. Okay? And just writing out what you're doing shows that you know what you're doing, first off. And if you make a mistake, you still get a point for running that formula out a lot of times. Okay? So that's equal to 950 minus 1190 over 3 minus 1. And if you're paying attention to units here, which are important for these questions, the units on the top numbers are liters per hour, and the units on the bottom are hours. So our answer is going to be in liters per hour squared. Oh, yes. Okay. And I don't know what that is. What is that? 100, 240 over 2, 120? Negative 120? Okay. That make sense? That's all I want. Okay. The next one is where we got to do like a left Riemann sum, and they're asking us, remember, Riemann sum always approximates an integral. So the integral of R of t, which is the rate that water is removed from the tank, should tell us how much water has been removed from the tank. That's what this value is going to approximate. All right. So we estimate the total amount by doing an integral from 0 to 8. R of t dt is what we're approximating. It's approximately equal to, we're doing a left-hand sum. So our first interval is 1, base of 1, right? Remember, we're just looking at this. Has a base of 1 and a height on the left side of that is 1340. Okay, so it's 1 times 1340. Plus, the next interval has a width of 2, so a base of 2 and a height of 1190. So 2 times 1190 plus. The next one's got a width of 3 and a height of 950 on the left side. Plus, and then 2 by 740. Everybody okay with that? Everybody know what that happens to equal? 8,050. Awesome. And what units are on there? Liters. Okay. And then they asked us this question. We haven't talked a ton about this. Is that an over or underestimate? Give a reason. So I told you. So we drew a couple pictures here, and there are some rules we can go over, and we can do that today. But just draw what this says. They usually tell you something in this prompt to let us know what's going on. And they're telling us that R is differentiable, but it's also decreasing. Okay? So if you're ever unsure if an estimate that you found is over or under, draw a graph of what they asked you to do and just decide to picture it out, okay? So if it's differentiable, that just means it's a nice smooth curve, and decreasing means it's headed down the whole time. Doesn't matter what else it looks like. So you can imagine R could look something like this. Okay? And if you were to integrate that with a left-hand rectangle, so let's say we're going from, remember we're going from 1 to 3 here, right? And then 3 to 6. Cool. If we made left-hand rectangles, it looks like this. Is that okay? Everybody see what I'm doing there? So do those rectangles over or under approximate that? Easily over. You can see it in the picture, right? Definitely an overestimate. And all you need to say is, because we used a left Riemann sum and R is decreasing. That's it. That's the rule. So we're going to write a sentence. This is an underestimate. Oh my God, thank you. Overestimate. It's going to be a long day. Overestimate since R of t is decreasing and I used a left Riemann sum. Okay? All right. Let's take a look at that C. I don't know if you guys got to C yet. Normally in C, they start changing things up. Maybe they give you like a whole new function, which they do in this particular case. Nope, that's a different question. They give us use part B to estimate the total amount of water in the tank. So let's snag that guy. So this is tying back, and I told you they do this, to kind of like a rate in, rate out question. Now we have the amount that went out, which it didn't really ask us to explain what it meant, but that's the amount of water that's left that tank. Everybody okay with that? So we integrated the rate out, so that's how much water has left. But it's an approximation to it, but that's okay. Remember we said to find how much is actually in a tank with a rate in and rate out question, you take the original amount. You're going to add in how much came in. You're going to subtract off the amount out. Okay? The original amount has to be given to us. Anybody know what that is?
50,000.
50,000. Cool. Plus the amount in. If they don't tell us that, they tell us the rate it goes in. So the amount in is the integral from 0 to 8. They give us a function for that. Of this thing right here. 2,000 e to the negative t squared over 20. dt. And you could put both integrals together if you want, but we already did the integral, right? We already did the amount out. Okay, so minus the amount that came out, which is our last answer, which was, I forgot already, 8,050. Okay, and notice, look, that's not part of my integral there, okay? My integral is just this, right here. So make sure you put that dt on there so you understand that. It's okay, it's 3 parts. What was in there, how much came in, minus how much left. And a lot of times we put the rate in, rate out together because we integrate them both together. But in this case, we already did one, so I just separated them out. You can always separate them. Sometimes they give you piecewise functions and you have to separate them. Okay? Yeah. So. Okay, that's wrong. So, and again, so you pay attention to units. That 8,050 is in liters. It's not liters per hour or minute, whatever units or time is the hours. Does that make sense? So it doesn't go in the integral. And that's always, guys, a dead giveaway to what that number represents and what you should do with it. Look at the units on the number. Okay? If you integrate liters with the dt at the end, you're going to get liters times hours, which doesn't make, we don't need that. We need how many liters. So we do that in a calculator. Anybody know what that integral is? Or what the final answer is, I guess? 49,786. Exactly? Oh, does it say to the nearest? Yep, it does. Cool. It's okay. So these questions they're not crazy difficult. You just got to remember, they keep over and over again. The integral of the rate of change is how much change has happened. Okay, they can disguise it a bunch of ways, but that you can see it. These questions they ask it over and over and over again. Because remember, that's the fundamental theorem of calculus. All right, and then the last one, which is right here. We can just write underneath it, I guess. Oh no, we're out of room. Let's do a new one. Okay, let me drop this down here at the bottom. So, let's just zoom in. Is there a time when the rate at which the water pumped into the tank is the same as the rate at which water is removed from the tank? This is a tough question. What are they really asking me to compare here? What and what? Rain. It's not when the total amount of water in the tank is 0. Okay, they're saying when the rate it's pumped in is the same as the rate that it's pumped out. They want the rate in function to be equal to the rate out function. Okay? The problem with that is we have a rate in function. We don't have a rate out function. We just have a table. So what are we going to have to use here? What's up? We don't need average rate of change specifically because we have the rate of change already. Like we don't need to find the average rate of change of the rate of change. Does that, you know what I'm saying? No, you don't like that? Okay. We need W of t, which is that what they call the rate in? To equal R of t. Okay. The problem is this is a table. Anytime you have to solve, so we have the table for R, right? If they ask me about R prime, now we got to start using AROCs. We got to start using average change. Okay. Anybody know what we're going to use to do this? Ideas? What do we use to say that a function from a table has to equal something? IVT. This is an IVT question. Okay, but they've disguised it. Yeah, it's tricky. Normally they're like, hey, does R of t have to equal 1,000? Now they're asking me, does it have to equal this function anywhere? All right, so here's how we're going to set this up. We use IVT to say that something has to equal a number, not a function. So we're going to move some stuff around so that we just have one function has to equal a number. Okay, I want one function equals a number, which means I'm going to move that R of t over and say, hey, does that ever have to equal 0? Okay, so rather than saying, you can go this route. You could say that R of t is below it, then above it. So they have to, it's kind of weird to word it though. If you move everything to one side, now all I got to do is show that, to show that this thing goes through 0, I got to show that W minus R is positive somewhere, and I got to show that W minus R is negative somewhere. Cool? Now, because they're usually, if you understand what they're asking you to do, they're usually pretty nice about it. All we need to do is find the values at the endpoints. If you find W of 0 minus R of 0 and W of 8 minus R of 8, one is going to be positive and one's going to be negative. That's just how they set these up, so that they don't want you searching all over the place. All right? The problem is, let me pull this table down here. I mean, if you didn't know that, then you got to hunt for this, but we got this going on here. Okay, I'm going to repeat what I just said. IVT doesn't tell us that a function equals a function. It tells us that a function will pass through a certain y value. Okay, so if at any point you have a table has to equal something, whether it's a function or a number, if it's a function, you want to move everything to one side, like I just did, and now we have a function equals a number. We can use IVT. Okay, but I got to show that it goes from above to below that. So I'm going to find W of 0 minus R of 0. W of 0 is 2,000. R of 0 is 1340. Okay, that's 660, but regardless of that, it is positive. That's what matters. It's above 0. It might also help us to name W minus R something. So does that make sense? Like, so it's just so we can call it one function, and we talk about this one function instead of two pieces. All right, so it doesn't really matter what you call it. Normally, like we call it A prime of t, right? Okay, so that's what I'm going to call it, where A is the amount of water in the tank function. Okay, so A prime of 0 is positive, is what we just showed. I'm also going to find what it is at 8. Now to do that, we need to know what W of 8 is. And if I know what W of 8 is, somebody calculate that out for me.
81.524.
81.524, thank you. And I don't know what that is when you subtract them, but you get something. And that value is most definitely going to be negative. 81 minus 700 is a negative value. Does that make sense? So now I have W minus R being positive somewhere, and I have W minus R being negative somewhere. So by IVT, it has to equal 0 somewhere. And if it equals 0, W and R have to be equal to each other. Okay, and I told you, D is going to be a weird question sometimes, so maybe you don't get all the points for this, all right? But if you can just, reason some of this out and get some in your paper, a lot of times you get partial credit. What's up, Hannah?
So can you just say if, like, W of 3 is greater than R of 3 and W of 6 is less than R of 6, they're going to equal each other?
I think if you word it correctly, yes, but it's tough. It's tough to write that out, okay? But yes, that's exactly the reasoning we need. Yeah. Yeah. You'd have to search around. Like I said, they don't want you guessing and checking all these different values. So they're going to make it pretty obvious if you know what you're looking for. It usually happens at the endpoints. Like remember we talked about when they make you do MVT? Like they say, does the derivative ever have to equal this value? It's usually just the average rate of change on that interval. Okay, but they could. You're right, and it would be a lot harder to find that. Okay. They wouldn't do that because then I just don't think they do that here. That's too much work. Okay, their goal is to make sure, do you understand what IVT is saying? All right, so we're gonna write this out, and this is a key thing for us. I'll make sure everybody understands this. Okay. Since now we gotta write this out. W of t and R of t always with the conditions. They're both differentiable, right? It tells us in the equation that R is differentiable. If they're both differentiable, and thus continuous, IVT is going to work out here. So I would say IVT applies to this situation, whatever you want to say. And now all we're going to do is say the function we have goes from above to below or below to above, and then it has to equal that value by IVT. Okay? So we have W of 0 minus R of 0 was 660, which is above 0, right? And that was above W of 8 minus R of 8, which was negative, I don't know, something. I didn't even find what it was. Just it was negative. Cool? So W of t must equal R of t. And I called it A prime. Well, actually, let's write what we have. W of t minus R of t equals 0 at least once. So W of t equals R of t at least once by the intermediate value theorem.